The only thing I use as camera photo is you guys, and I paid for it out of my pocket. So, okay. Maybe that's enough about p-value, so we'll come back,
Yeah, maybe
talk more, that there's more to the conversation. But yeah, I don't think your intuition is failing you. I think it's your mathematics and your interpretation about the actual, like all the details in the math. I think the details are important. Is that at least kind of fair?
All right.
For now.
I'll try not to worry about it.
Well, if you do worry about it, you're gonna turn out like me. So it's a slippery slope. I used to worry about this a lot and think about it quite a bit. I don't think all the problems and issues have been solved out there. I kind of just don't like the point null test. But if you are going to do it, you need to specify effect sizes and calibrate to your alternative hypothesis. More on that tomorrow. So we're right in the middle of the conversation. Your other questions are really good, so I can answer those a lot easier. So, but let's come back around to those in order. So let's just run down the list, unless there's anything we want to add. Good idea, Eric. So model averaging, I would like to add a lecture on that towards the end. I think that's a good thing to slot in. And it works out, it's real easy. I can tell you what it is in 10 minutes after I get through the next couple weeks worth of stuff. So yeah, remind me of that. Okay, other questions? Okay, could you please show some details of problem 5 of the midterm? No problem. This is a pretty easy problem once you've run through it a couple times. But problem 5 of the midterm, I think I can do that in a minute or two. It says something like this. Y's are coming from a normal distribution with mean x beta and variance sigma. Is this about right? So this is a shorthand way of writing it, but that's it. The only difference from what I'd done on a previous homework is we had let that be sigma squared I. So that all of the y's were independent of each other. So it's a diagonal matrix. So the midterm problem and the homework problem early are exactly the same, except that's dense. So all of the y's are correlated with each other. We could do more than one data point, but this is a vector right here. And so we could do it just for one data point, that's fine. This is a standard regression model. So sometimes people refer to what we get out of this as weighted least squares. So all we need to do is just write down our likelihood function for beta. And so this looks a heck of a lot just like the sampling distribution. So what does this look like? This is going to be sigma to the minus 1/2, e to the minus 1/2, y minus x, beta, transpose, sigma inverse, y minus x beta. So you don't even need this because we're not doing inference on sigma, but if we were trying to infer sigma, we would need that. Since we're just looking at this, and sigma is a constant in all of this, which I ended up stating, it's a known constant. If it weren't known and you wanted to infer them jointly, you'd probably set up a given sampling to do it. So, and then integrate everything out, you know, using that Wishart formulation. You could either go to a t distribution directly, or you could run your give sampler and it would pop out for you as t distributed without you even knowing that. So I'm going to multiply by my prior. I said that's proportional to 1. I could have used the full-blown conjugate prior to make the problem a little bit harder. But once I do that, this is now my posterior distribution. So my posterior distribution is proportional to the likelihood because our prior is flat. So keep in mind in this model, X is considered known. And so while it looks like beta is a scale parameter with respect to X, X is known. So this is really acting as a shift parameter with respect to Y. So that's a little bit different. So that's why the flat prior makes sense. So same exact thing as before. So I'm just going to expand everything here. So this is going to be Y transpose Y. We'll do the interior term. So this is going to be this one times the transpose of that. I've already made a mistake. I have this right here and you can't get rid of that. So this will be sigma inverse Y. So that's Y transpose, that one, times sigma inverse times that Y. So then we have our, I guess our cross terms right here. I guess I'll put in both of them just to discuss them for a second. So I'm going to have minus beta transpose X transpose. So I've transposed X beta. When I transpose X beta, that's the same as beta transpose X transpose. So you flip those things around. So times sigma inverse times Y. So that's one of my cross terms. Let's do the other one as well. So it's going to be Y. This will still be a minus. It'll be this minus sign. Y transpose. So that's transposed. Sigma inverse times X beta. So that's our two cross terms. And then we have this last term right here. So again, when I transpose X beta, is beta transpose X transpose, sigma inverse times X beta. So we do the exact same thing we've done on all our other problems. We recognize our quadratic term. So this doesn't help us at all right here. This is just a proportionality constant. We can pull that through, factorize it out. This term right here, let me just ask the question, what's the dimensionality of that? So 1 by 1, it's a scalar. Everything up there is a scalar. It's all just scalar stuff. So that's a 1 by 1. This is the transpose of that thing. The transpose of a scalar is exactly the same thing. So this whole thing is minus 2 beta transpose. I like to recognize it with a random variable sitting out in front. So if you like to recognize it in the other way, totally fine. X transpose sigma inverse Y. So there's my minus 2 linear term. So just like before. Look at our quadratic term, and we notice that everything that's multiplying our quadratic term, the inverse of it is the variance. So I said it a little bit different than I said it when we were dealing with the scalars. But this is a quadratic form. If we thought about this as a scalar quantity, this would be beta squared. And then I would have something that I'm dividing by, and I would have to flip that thing over. The way we say that in terms of linear algebra is I take my quadratic factor and I just invert that thing, but I do it in the way that makes sense. I don't divide by it, I invert it. So our variance for beta, I'll use shorthand notation, tell you it's a full conditional. Basically, it's the only conditional in here because sigma is known. This is going to be equal to X transpose sigma inverse X inverse. And that's it. Before, this would have been a sigma squared times I, so that little sigma squared would have floated right out here. But we've got that thing buried in the middle. The expectation is very similar. I'm going to multiply this stuff by this thing. just like we did before. Which way is the correct way to multiply it? You'll have to check the dimensions and see what makes sense. So I'll let you do that. X transpose sigma inverse y times X transpose sigma inverse X. Is that it? No. How can you tell? It doesn't make any sense, the dimensionality of it. So you do it the other way. X transpose sigma inverse y. So if you went through and you checked the dimensionality, or if you tried to plug it into your computer, you would get nonsense back the other way. So that's the answer. So pretty straightforward. So Ruchin, same problem, dense covariance matrix. Please illustrate a little bit on the Gibbs sampler. Problem 1, homework 4. I didn't figure out how phi is connected to the other two parameters. Good question. So, everybody ready for this one? You know what Ruchin's question is? He wants the full conditional for phi, and he doesn't understand how that's connected to the other two parameters. What are the other two parameters that he's talking about?
Alpha 0, beta 0, sigma inverse.
Phi is sigma inverse, so it's totally related to it. And it is, but those are hyperparameters. It's the theta naught and the sigma. The cap sigma. Is that what you said?
The big one.
Yeah, the big one.
Okay.
Okay, we're on the same page. Model looks like this. Let's just write it down. We've got our WIPs are going to be normally distributed with, and I'm going to write it down like this. Maybe theta I transpose times 1 T. So this is going to be alpha I, beta I transposed. No, I guess I like it like, so that's going to look like this. So I have everything defined as a column vector. So theta I transpose is just that times this. If you multiply that into this, this will be alpha I plus beta IT. So precision parameter is phi. Theta i's are random effects. They come from a normal centered at theta naught. Covariance sigma. I'm going to put it on a precision scale, if you will. And that's basically our whole model. We'll need some priors on all of this. So we'll need phi is some gamma. Call it whatever you want. So these are priors. I'm going to do my prior on sigma inverse. Let that be a Wishart. You can pick your parameters for that if you like. We don't need to do that until somebody asks me about this layer of the problem. But for phi, updating that, we don't need those, which is exactly Ruchin's point. So where does this stuff come in for phi's full conditional? Still like his question, that how is it dependent? It is dependent, but not directly. It's conditionally independent. And then we need a prior on theta naught. So it's going to be some multivariate normal. You can pick some hyperparameters for that as well. So if we want to work out the full conditional on phi, we write out what the likelihood looks like. this is going to look like this. I goes from 1 to n. This will be for rat I. This will look like, these are the W's right here, so this will look something like phi to the 1/2, e to the minus 1/2, WIT minus theta I transpose 1t squared, and then I have a phi up there. So that's rat I's distribution. Does that look right?
The product over all the days as well.
Over all the days, yeah. That's right. I probably should do that first. Yeah, you're right, because there's this part right here. So yeah, let's do it over all the days. So this is the rat I's time series, is what I mean. This is a touch superfluous, but let's write it down anyway. So times what rat I's parameters, the probability of those parameters are, aka the density. So that's this layer. So I need to product over all the different rats. 1 to n. And so this will be this distribution right here. So you could write down the sigma 1/2 in here. You probably should keep that term in there, so when you're updating this thing, I'm going to throw it like that, the -1. So I would leave that in there because it is a parameter you're going to have to touch. This equation is something that you're going to probably stare at in every step of this problem. So e to the minus 1/2. This will look like theta I minus theta naught transpose sigma inverse theta I minus theta naught. Sometimes people call this the complete likelihood. I just call it the likelihood. So it's got all the layers of the model in there. Regardless if we're Bayesians or non-Bayesians, this is the model. There's a random effect model. And so while the distribution on theta I feels like a hierarchical prior, and in some sense you could say that, but you probably wouldn't want to conflate why you're doing it with these things right here. The reason we're specifying these priors right here is because they're conjugate, and maybe we have some limiting properties of these priors. Maybe these are all Jeffreys priors. They are. So this is being done so that we can model the specific groups and the inherent variability in all those specific groups. People that touch random effects and don't go all the way over to being a Bayesian will, eventually. In my 20 or so years of doing this, I've noticed that a lot of people touching random effects models just end up just doing the whole thing as MCMC, because if you're gonna computationally infer theta I through a Gibbs sampler, why not do everything else as well? Anyway, you've noticed there's a lot of overlap between Bayesian thinking and non-Bayesian thinking, and in terms of point estimation, it's very similar. So, okay. Anyway, that's what we've got, our complete likelihood. So now I want to take this thing, I'll call it a star, and use this to figure out all our full conditionals. If I wanted the full conditionals for theta I, we're already ready to go. It's already here. So you can work out the quadratic form in terms of theta I and get that full conditional for theta I. So the Bayesian would call that a posterior distribution for theta I. in a non-Bayesian might call it a random effect distribution. So it's all in a name. How much are we going to argue about that? A lot, apparently. So people can't help themselves. Okay, so if we wanted the full conditional for phi, we're going to take star and multiply it by our prior distribution. So this will be star times phi to the, I'll call it alpha naught minus 1, just because I already called that alpha naught. I'm not sure if that's the same notation in the paper. It may be. Times e to the minus beta naught phi. So I think what is confusing is this whole part right here just falls out. This doesn't have any phis in here. So if you work this whole thing out, this thing doesn't show up, and this thing doesn't show up. So they're conditionally independent of those. So the inference on phi, what is phi connected to? It's connected to the theta i's. The theta i's are connected to everything else. So there's kind of this linking between information. Not everything is jointly conditional on each other. There's these layers to this. That's how all hierarchical models look. And so for this right here, we don't even need this part. There's no phis in here, so this is all part of the proportionality constant. But when we go to update the theta i's are going to appear here, and they're going to appear here, and it's going to bridge everything together. And the theta i's are certainly dependent on the phis. But the phis, it doesn't go the other way. So it's kind of interesting. So what we would do is this is going to be proportional to this stuff right here, but I do have to remember this product right in here. That product is also part of it. And so that doesn't disappear just because this is all proportionality constant. And so phi has something to do with all the variability in the t time points for all n rats. So phi appears for all of them. So if you were to sample this data, you would have touched phi t times n times when you sampled the data. For every rat, for every time point, phi was involved. And so this will look like this. This will look like phi to the n times t divided by 2. That's here. Just taking that product across, and then I have e to the minus 1/2, and I have a double sum that appears. One is over I, one is over t. So this will look like, I'll put the phi right here. So I'm just looking at this part right here, and then I've got all this w I t minus theta I 1t squared times this stuff right here. So this is going to be plus alpha naught minus 1. So this part was all from likelihood, and that part's from our prior. And then I've got this part also. So this will look like the 2 only goes with this part over here, so I'll draw the 2 over here. Try to clean that up a little bit. This is minus p. Put that in a brace. All I did is pull the 2 over there. Plus beta naught. What distribution is this? This is a gamma. Which gamma is it? We can recognize all the parameters. nt over 2 plus alpha naught plus all of this stuff. Oops, not plus. Comma. Double sum in here over I and t, wit minus theta I 1t squared divided by 2. Just be specific about this. We don't sum up the beta naught. this always kind of irritated me, like when I was in college, and I'd be looking at stuff and it's like, where does the brace end? So where does the sum hit? And everybody's a little bit different about that. So I've always wondered, why don't they just include braces every single time you open a summation sign? And now I'm here doing the same stuff. So I'll close that brace right there, plus beta naught. So the sums don't hit your beta naught over and over again. Keep in mind, you only have one prior. It doesn't come in for every time point. So again, back to the original question, what does this have to do with theta naught and cap sigma? Well, something. So it depends on the theta i's, and the theta i's depend on the theta naught and the sigma, but not directly. So they're conditionally independent of each other. But if you ended up updating everything and you're running through this Gibbs sampler, all that information is propagated through the full conditionals. So it does come into play, but it's after you just start iterating over it over and over again. So it's conditionally independent, but it's not independent. There's a difference. So provided the theta i's, if we looked at this, they're independent of everything. But the theta I itself is not independent of theta naught and sigma. So if I gave you theta i's, then you wouldn't need that information. But keep in mind, we're jointly inferring all of it, so when we run through a Gibbs sampler, everything is jointly dependent on everything. Just not all in the same full conditional. Does that kind of make sense? I mean, I know the question asker isn't here, but does that make sense to everybody else? I kind of like that, you know? So it's like, when I look at this equation, and this equation we're going to look at for working out all the full conditionals. Let's just think about this. If we wanted the full conditional for theta naught, this part doesn't come into play. Right here, this is all proportionality constant. And in fact, this product right here doesn't even come into play. So this whole piece right here is a proportionality constant with theta naught. So keep in mind where this product is, where that brace is. It ends right here. So this isn't producting up anything to do with the theta naughts. So for theta naughts full conditional, you've got this piece, and that's the only product. And this piece is conditionally independent for the theta naughts. But again, for the same reason, the theta naughts and the theta i's are tied together. The theta i's are tied together to the phi. We could do the same thing with cap sigma. I'd probably do it for sigma inverse because that appears right here. But exactly the same thing for sigma inverse. This whole piece is just proportionality constant. So if all these are known in that layer of the full conditional in your Gibbs sampler, this is just all proportionality constant. So that falls out. But everything is tied together. If you found some parameter that you were inferring and it never had anything to do with the data, your model doesn't make any sense. But all the parameters involved in this have something to do with the data. Maybe not directly, but through kind of a chaining effect. I don't know what the technical term is other than conditional dependence. Does that make sense? Good question. I remember when I saw that, I was like, that's really cool. You know, you model all kinds of stuff using this sort of technique. Okay, so the connection is there. It's just not there directly. But when you write down all the full conditionals and you iterate over it, everything depends on everything. Shushan? Shoot. So, could you please point out what you want us to compare with the paper? Could you please talk a little bit more about Markov decision process and Markov chains? What I want you to compare with the paper is just the results. Did you see the results section in the paper?
Why would you put figures after the model?
It's crazy, isn't it?
It took me like a week to find it.
Yeah, it's crazy. They don't table the results what they do, here's the paper, is they, at the very back of the paper, they have a bunch of pictures of all of their parameters, if you can even read them. And so this is the extent of their stuff. So what I want you to do is do the eyeball test and see if they're just approximate. What I really want you to do is play around with your hyperparameters and your priors and see if it makes a big difference. And then just tell me about that. So I think they did a thoroughly horrible job in demonstrating the results. What they did a good job is exemplifying the utility of the Gibbs sampler in this paper. And this was the prelude to their big Gibbs sampling paper. It's very clear to me they're not really interested in the scientific inference that they're doing. They're interested in highlighting the utility of a Gibbs sampler. And they're probably really excited about that. And if I were them, back then, I would probably be too. Nowadays, that wouldn't be something that you could publish. You'd need to put down a table and actually give real numbers. But you can eyeball those distributions at the end, and you can say a sentence or two, how much do your hyperparameters influence the results? So try a hyperparameter setting or two. And really, if you just wanted to report something to me, show me your trace plots. And if you want a table like your posterior mean and your posterior variances, you could do that. But you could just show me the pictures, show me trace plots, and draw me the densities after burn-in. I don't care about the burn-in part. They say that they converge in like 35 iterations. Good starting points. So nobody knew anything about anything back then. So, you know, the bar was pretty low, but as people started to play around with this, the bar has come up, and now people want you to detail the numerical accuracy of everything so that it's repeatable. But again, I think what they were doing is highlighting the utility of the Gibbs sampler, and we're all appreciative of that. That's a huge thing for all of statistics, I think. It at least pushed the envelope a little bit further. So show me trace plots and show me some densities. And then write a sentence or two and say how much they agree with what you saw in the paper and how much the hyperparameters influence things. You had a question about the gamma 00 or the inverse gamma 00. Was that you?
Yeah,
So you said, could you talk a little bit more about their hyperparameterizations for their priors? So those were all these things right here. I think they used an inverse gamma and not a gamma, but it doesn't matter. And these parameters have exactly the same meaning when you invert everything. So reference Wikipedia, or just do the transform yourself. So a gamma 00, if I transform it, there'll be an inverse gamma 00. You'll have to interpret those parameters a little bit different. They're not always defined on the same support. No surprise, when you flip things over, sometimes bad things can happen. So I like using the gamma and not the inverse gamma. So if you didn't like the 00 and the inverse gamma, you probably don't like the 00 and the gamma as well. I think the specific question is, isn't that outside of the bounds of support for that conjugate prior? And that bothers you, right?
it caught my attention.
Yeah, it should. So let's look at what a gamma 00 looks like. And this might look familiar to you. So let's say I did a gamma 00. This would end up looking something like this, proportional to, let's say phi was this, would be phi to the 0 minus 1, e to the minus 0 times phi. Okay, so that's alpha, that's beta usually. That's 1. That's 1 over phi. Connection. So yeah, all those Jeffreys priors are limits of conjugate priors. Not all of them out there, but the ones we've discussed in class are limits of conjugate priors. And in unbounded spaces, they tend to be improper. And that kind of makes sense from the viewpoint of you don't want to stick too much mass in any one specific place. So where does that come from? Where's the next connection you make? You say, oh, that's the scale invariant prior. So that's the one if you didn't want to inject any information about the scale. So it's an improper prior. So what Bayesians are usually doing is not applying Bayes' theorem directly, but they're applying a limit of Bayes' theorems. They're using the format of Bayes' theorem, but they're not using it directly because it's not a probability distribution. So you're right, it's not a probability distribution, and this was kind of the conversation a couple months ago. Probably a couple months ago, that would have bothered you a ton. And now, after doing it and kind of playing around with it, you're like, oh, it kind of works, kind of makes some sense. That's how Piper feels. So, that's how I feel.
So then going off that, the sigma inverse equals to 0 is the flat prior.
Sigma inverse.
For the normal, for the theta naught as normal, they used notation was
Theta
theta
zero.
inverse
Yeah.
0.
Which one is it?
For the theta naught prior,
Uh-huh.
they said that basically that sigma inverse is 0.
Yeah.
So it's equivalent.
Yeah, they're making it a flat prior. Exactly. So it's like taking the variance and blowing it out to infinity. Same thing. Yeah, so everybody uses language that's a little bit different from what I might say in class, but we're starting to make those connections.
Is there a limiting version, like related to the Wishart?
Oh,
Okay.
yeah.
I couldn't figure out what it was.
It's the one in your homework that I gave you.
Oh.
Remember that determinant of sigma
Oh.
has the dimensionality plus 1 divided by 2? It's that. That's it.
Because I suppose the one.
Yeah, so that one where you integrated against that determinant of sigma, or sigma, well, I guess the way I wrote it was sigma, so you were using the inverse Wishart. That is the Jeffreys prior. Okay. Moving right along. Anything more about the rat problem? So I'm not looking for you to do anything excruciating, Shu. Just kind of eyeball, make sure your code is working, and then tell me what the impact of your hyperparameters are. And my recollection is they kind of matter. And so I would say in any analysis where you wiggle your hyperparameters around a little bit and the posterior moves around the same degree of a little bit, you've got some explaining to do. So again, I think that the utility of that paper was to highlight the utility of the Gibbs sampler, which back then was totally brand new. Okay. A few more questions. Shu, anything more about Markov decision? I'm not sure. I could talk about it for a whole class. I mean, like a whole semester, I could talk about MCMC.
Actually, nothing special, like, because I haven't touched this part before, so I just want to get some basic knowledge about this part.
One thing that's kind of interesting is I'm just asking you to Gibbs sample everything, and you can Gibbs sample everything directly. If you didn't have a Gibbs sampler, you could, if you didn't know how to sample from the full conditionals directly, you could set up the Metropolis-Hastings decision rule. It would take you longer to converge, typically, unless you had really good proposals. You know, even though the acceptance rate for Gibbs sampler is inherently 1. So one thing you can check in the Metropolis-Hastings decision rule is if you use the full conditionals as your proposal, your acceptance rate from that Metropolis decision rule is 1. So you'd be taking the min of 1 and 1. So if you use the full conditional as your proposals, and you drop that into a Metropolis Hastings decision rule, you would always calculate the exact same acceptance rate. It would always be 1. And you can kind of figure that out, that the full conditionals and the total distribution are the same up to proportionality. So it's one line proof. So there's at least kind of a connection. Cool. Let's see. Let's jump to Anna's question, more of a calculus question. This is a good question. So, is to, when we integrate it over everything, we integrating it at a point, and shouldn't that whole integral be 0? So let's just remember which integral we're talking about. I remember thinking this for a long time. That makes sense to me. So if I did this, let me just write down, this would be 1 over root 2 pi sigma over root n e to the minus 1/2 x bar n minus theta squared over sigma squared over n d theta. And if I ended up integrating from theta to naught, that thing is 0. That's true. So, but that's not what we wrote down yesterday. Wrote something just slightly different down. And so the mass contribution of this one point compared to the entire continuum, so keep in mind what this whole function looks like, centered at theta, right there. So this is the distribution, the margin over x bar. And wherever theta naught is in all of this, so let's say any point that I was going to integrate this thing against theta naught, right here, the area of that one little point would be so negligible compared to anything else that we'd be averaging over that it would contribute nothing to the sum. We're all pretty comfortable with that. So this is a little bit different, because what I wrote down was this. And so what we're really thinking about when we do this is an infinitely tall point mass on everything.
I thought that it was just a delta equals 1. 1 or 0.
It's a 1 or 0. Yeah, but what I talked about, if you thought about it as a density function, what would that mean? And so as a density function, if we thought about it as an actual probability distribution, this Dirac function, it would be infinitely tall with 0 mass, and it would integrate to 1. So we're kind of talking about the integrated value when we write this down. So Anna's asking me a measure theory question. It's a good question. But this thing is actually infinitely tall right here if we were integrating over it as a density. But if you wanted to think about it as just this indicator function, you might think about this. So if I were to redo this and go from minus infinity to infinity, it's the same thing, because this is only going to take on one value of positive mass and 0 everything else. Now it's not the case that this one slab, this one little spike, would be negligible compared to everything else, because everything else we'd be summing up is 0 compared to it. So this is 0 everywhere else. Regardless if we're talking about the infinitely tall point mass or we're using it just as an indicator function, everywhere else it's 0 on everything. And so that's contributing no mass anywhere else. And so this thing does have mass. But in a measure theory class, they would probably treat this a little bit more carefully. But if you didn't like any of that, and you wanted to work with, let's say, some sort of a normal distribution or some sort of distribution that got peaky around theta naught, and you took some limit of this integral that you're playing around with, you would converge to the thing I wrote down yesterday. This would end up being, this would be the only thing that contributed any positive mass would be that point at theta is equal to theta naught. So this would be 1 over root 2 pi sigma over root n e to the minus 1/2 x bar and minus theta naught. Because that's the only place it takes on positive mass compared to everything else. So everything else is 0 in there. So yeah, when I was saying it's the easiest integral in the world to do, I may have been misleading you that you thought it was going to be 0.
I know that one.
Yeah, that would have been cool too if that was it. But really the real thing is, if you thought about this as a density versus just an indicator function, it's infinitely tall and infinitely skinny. And if you wanted to work through that in terms of a limiting argument, you could use a prior that kind of did something peakier and peakier around theta naught, and it'd end up converging to that. And you could check that. So I was trying to brush that sort of infinitely tall sort of thing. And back in the early days of constructing all of this, Dirac needed to justify that this point mass was an actual proper distribution. I guess it abides by all the axioms of probability just fine in a limiting sense. There are people that don't like to use the actual point mass itself, and what they'll do is they'll take something that's super peaky right around here, and in the alternative space, they'll have something not that peaky. So that's called the spike slab formulation of the prior. And so people kind of like that a little bit more, that you're not working with a point mass and that you're calibrating the two variances to each other. And then people ended up proving basically the analyses are exactly the same when you do that. So that if you end up making this real peaky and you use the other thing as kind of a diffuse slab, you get about exactly the same results that you would get if you used a point mass. So I prefer the point mass, but some people like to use the super sharp normal instead. In the limit, they're the same. So that's a good question. Something I didn't explain all that well. But if you broke this up into Riemann sums, and it only took on positive mass right there, and you did that limiting argument, you would see that this is the only place it has any positive mass. And so using that limiting argument, the Riemann sum argument, you would come up with that, because everything else is 0 in all those other rectangles. Is that going to make sense? Let's see. A couple more, Nathan. So hyperparameters, p-values, normal distributions. This one could go on for a while.
Right, yeah, we want to talk.
Let's talk after. So, but the height thing is an interesting question. So you wrote in, it seems really weird that nature would, without very many averages. So you're thinking about your mom and your dad are the averages, right? You're averaging their behavior to get your height. So your parents are probably not both shorter than you.
They're both further than me, actually.
They are? Okay. That could happen.
Present convince
It is a probability thing.
Right.
So I think it's not IID. So in nature, that sort of averaging process isn't an IID thing, but the average is happening over generations and over the whole population. So that's how you would think about that. And so that normal example for heights that everybody gives, and that's what I started out learning too and thinking, oh, that's really cool. It's not IID, but there are other forms of the CLT.
Right.
So, and that spurred lots of interesting conversation back in the early days. But yeah, sometimes I use normality just to indicate that it's centered somewhere, and then I believe to the right and to the left equally. But I am usually careful about my tail behavior, and I'll usually use something like t-distributions if I were just being really cavalier as a modeling thing. I said, oh, there's symmetry between this, and I'm just kind of trying to model something that's centered around here. But I usually am pretty questionable about that exponential tail behavior. It's really subject to outliers. So if there were any outliers, I'd want another lever in my model to pick up the tails. So normals pop up a lot because of the CLT, but sometimes people just overly generously use them because they're convenient. So finance was this way for a long time. So the Black-Scholes thing, I know that they didn't say Gaussian or normal and all of that, but they said diffusion. And so all that diffusion equation stuff, it's like Brownian motion, and it has a connection to the Gaussian distribution. So they're distributed the same ways. People used to assume that the drift on stock markets and things like that were normally distributed. And they got to find out very painfully it wasn't that way. 1988. So lots of people felt so strongly about it and were so surprised about it that, well, you can read the old history books on that. That was a bad day. You know this story, right? So Black Tuesday, is that what it was?
Not specifically.
I remember my woodshop teacher coming in tears. I'd never seen like a grown man cry like that. So he's like, I lost everything. So people are like jumping off of buildings in Wall Street because of it. So what have we done away with? Black-Scholes. So a lot of things that are normally, you want to think of as normally distributed, probably a Cauchy distribution would be more appropriate if you want to be careful. Stock market isn't anything like that anymore. So since the internet, so there's not information diffusion. But anyway, sometimes we just use normality as kind of a starting device. So if you're trying to model some sort of regression, it might have something to do with normals, but it might be mixtures of normals, you know, whether or not they're location mixtures or scale mixtures, but a lot of times you can take everything you learned about normal theory and extend it to other distributions. And you've seen a couple examples like that. So turning normals into t's, for example. They're the scale mixture. And there's other mixtures out there as well. So they're good starting blocks. That's how I think about it. So Poissons are kind of the starting block for counting distributions. Exponentials are kind of the starting block for like memory list type stuff. So, but it's not, sometimes you might say, well, it's not memory list, so I want to do something different. But there might be a layer in your hierarchical model that has the exponential distribution or the Poisson. But then there's other layers to your hierarchy that make it more realistic. So, and if you write down models like that and you want to learn how to infer from being a Bayesian and doing Gibbs sampling is super useful. So it used to be that everybody would work out the asymptotic properties of their distributions, and then they would test everything against these distributions, and people started thinking it's more complicated than that. You know, that distribution isn't quite right, the tail behavior is wrong, or it's skewed a little bit. And so you'll start bolting on these other layers to your hierarchical model to characterize the data a little bit differently. That's how a modern Bayesian operates. So it's kind of cool. So what I do is I start with some basic model, maybe normality. I fit everything, and then I look at maybe my posterior predictive distributions. I take a holdout sample and I see if my posterior predictive covers my holdout sample, and if it doesn't, then I go back to my model and I start adjusting it. And I start looking at where the residuals are and why they appeared that way, and then I'll build more and more realistic models until I get something where the posterior predictive kind of matches my holdout sample. So I always do leave one out. So I just pull one thing out, build a whole Gibbs sampler for everything but that one data point, and then I use my posterior predictive from my MCMC samples that I've gotten out of my Gibbs sampler. I form the posterior predictive, and I see if my predictive intervals cover that holdout point. It's an exhaustive process, and I enjoy doing it. So, and when all of a sudden the posterior predictive distribution doesn't start covering my holdout sample, then I start modifying the model. So who am I? Am I a Bayesian or a frequentist? Kind of both. So that holdout sample and checking to see if I'm covering it is entirely frequentist. It's kind of interesting. So here's a fact, that if you have a prior distribution, I always ask my students to debug their code this way. If you have a proper prior distribution and you can sample from it, so I sample from my prior, I plug into my sampling distribution, I generate synthetic data that kind of looks like the problem I'm playing around with. You form the posterior distribution for the parameter, and if that parameter doesn't cover the parameter that you sampled out of your prior, 95% of the time, if your 95% intervals don't, you have a bug in your code. So I'm taking a frequentist property that I know from everything, and I'm using it to check my Bayesian code. And I'll also use frequentist properties to validate whether or not I think the model is correct. And so I use frequentism when I think it's appropriate, especially when I can test things over and over and over again. So it's kind of cool. And you can do that for all kinds of complex data. It doesn't have to be IID, but in the IID case, it's really easy. So there's my Bayesian, non-Bayesian compromise. Anything else? Everybody feel strong?
I think for a lot of us, get the sense that we are interested in some of the practical details of how to actually assess convergence of some of these samplers.
Yeah.
And that, I don't know about, we covered in lecture, and there were some tidbits that seemed very interesting, but I think that's basically where a lot of us would like to place some mass in terms of so what we're doing.
My presumption is that most people in this class, this is their first real deep dive into Bayes. And so it's kind of like the first survey course in something that you would expect to get. So I do teach a Monte Carlo class. It's specific in lots of different Monte Carlo devices, not just MCMC. Hopefully I can teach that again soon. And we go into lots of depth. My very early feeling on this was I wasn't going to teach anything practical in this class. This is me 17 years ago, coming out of graduate school. I'm thinking, no, this should just be a theory class, and I'm just going to do measure theory and limits. And then I thought, you can't really be a Bayesian without running a Gibbs sampler. So I'm going to give you guys some more practicality. And then I started getting people from out of department, engineers, scientists, and I thought I wanted to cater to everybody. So it's a bit of a hodgepodge, and if this provokes you to go take the advanced Bayesian class, do that. And the MCMC class 5314, if I don't teach it soon, probably Higdon will. So take that class. So there's a whole spectrum of classes you can take.
So in this course, some of the analyses we do are not expected to be very simple.
Say it again.
In this class, if this is where in this setting, some of the analyses we're doing without trace plots or things.
Yeah. If you just get the semblance of what a Bayesian does, how they operate, that's my goal. So that you could have conversations with somebody that's doing this modeling, you know what full conditionals are, you know what Gibbs samplers are, you kind of know why they work. At least you've experienced them and gotten one up and running. I feel pretty good about that.
We are going to focus a bit on theory. Might we also address, I don't know how difficult the question is yet, but why you claim that Gibbs samplers remain within a particular contour as they're converging. I believe you made that assertion that once they've entered a certain contour of...
Once they converge, they stay converged?
Yes.
So you want me to prove convergence of it? So I wasn't going to touch that either, and I don't even do that in my MCMC class, but they're almost sure converging. So I don't actually touch that, but if you did get a more advanced book, and if you swing by, I could probably give you one that could run through that if you're really into that kind of stuff. It's an important thing, but no, I wasn't gonna, if I start proving things like almost sure convergence or convergence in probability versus, we have to go through a lot of examples that involve infinity. And my experience is that I'll confuse more of you that you do not understand what infinity is. Because that's kind of the differentiator in all those examples. And so if you have a lot of practical common sense, but not a lot of abstract math ability or experience, you're going to be thinking, that just doesn't make any sense. And there's a lot of problems like that with infinity. So I try not to touch it. Let me give you guys a gift. I think we can extend the due date on everything. If you do a nice job on the MCMC and compare to the paper, and you need a little bit more time getting things up and running, you could give it to me the day after we return from Thanksgiving break. So, but try to stay busy. So stay on it. I'm going to give you guys some extra credit for over the Thanksgiving break as well. So if you guys need that, you'll have an opportunity to get some points there. So some of this stuff that you're implementing can be a little bit difficult. I'm surprised that nobody asked me about the Bayesian calculation for testing the 4 hypotheses.
You have I noted that at the start of this lecture you said you weren't going to post this year's review session, so I guess just that there's a review session from a previous year where you reviewed some of the numerical inaccuracies that were wrong.
I'm glad you found that. That makes me happy. You're a good researcher. I mean, so it wasn't supposed to be a super secret, but yeah, there are some numerical issues in that. So spend some time on that and get started on it, so maybe you can ask me some questions before Friday. Sound good?
I have a question. Will we learn how to set the prior for the hypothesis testing tomorrow?
I'll tell you what you need to be aware of, but I'm not going to tell you what to do, per se. I can tell you at least what to be aware of and what the issues are. There are, what some people will do for calibrating the variance is they'll use a holdout sample from their data. It's something called a minimal training set, and they'll end up calibrating their prior to the minimal training set. And so that's an empirical way that people do that. Again, advanced Bayes. So some of this is just to point out what the issues are, what you should be thinking about. But how do you do it? You need the context of the problem, is what I'll always go back to. I'll read you at least an excerpt from Jim's book on it, things you need to be aware of. But I think you need to be aware of how far away from the null you want to be before you would be willing to reject it incorrectly, you know? And so that's a specific question that probably needs to change for every analysis. So I know you want a prescription, and I know that's what everybody wants, and that is the problem with everything. So I think about this when I'm like in my car, you know, and I'm like trying to get like the bird crap off my windshield. And I'm like, I just want automated control over when the windshield wiper starts going back and forth after I've like had all the fluid go all over it. I need the fluid to sit there on it for like 10 seconds to dissolve it before I hit it with the windshield wiper, but you guys know what happens. The fluid goes onto here. So it's like, I want control over this thing, but how often do I want control over that? Periodically. So there's this trade-off between automation and having total control over everything. I know people want automation. So they don't want to be told that. You tell them that and they'll freak out on you, but it is what they seem to want. You can think about if you're different. Here's another answer. Standardize all your data. Put everything on standard scales. And then, you know, maybe using an alternative variance of 1 maybe makes sense, or an alternative variance of 2, or something like that. You'll see cheap answers like that. So what do? If I don't have good answers to that question, I don't hypothesis test. So I will talk somebody into something else. One of my favorite, in getting reviews back on papers is hardly my favorite thing to do. Anybody that's ever gotten them back knows exactly what I'm talking about. But I really like this snarky comment from a reviewer that said, this guy just is doing everything he can do to avoid hypothesis testing, and I really just want the p-value for this thing. And I was like, yeah, at least he noticed that going out of my way, doing predictive analyses, doing everything except for what they've asked for. I didn't want to do the hypothesis test. I didn't think it was meaningful. Without somebody telling me something about how far they would have to be from the null before they thought that was meaningful. So I'm never going to tell you what to do and go.
So for 3B, we need to set the prior for the hypothesis testing, right?
You do. Oh, you're asking about that specific problem?
Yeah, right.
Oh, okay. I can answer questions and specific questions, but I can't answer, okay, so the prior for, what do you think it should be?
Normal?
Maybe normal. So keep in mind, let me just write this down for those of you who are watching. Homework due Monday after Thanksgiving.
28th. Yeah, November 28th, according to Sarah.
What day is it?
November 28th.
Cool. So, should make us feel a little bit better. Okay, the prior. So let's just check this out. H naught is theta could be, let's say 10, or H1, theta is an element of 15, 17, 20.
Yeah.
So this is not a continuum. So let me just point that out. So if we picked a normal, we'd be expressing prior beliefs about things between these numbers. And so we want to limit our attention to these 4 different numbers. So let's try again.
Uniform discrete.
Yeah, how about just a discrete prior? So maybe this. So pi theta, this might be your total prior. It looked like this. 1/4 delta function, theta is equal to 10, plus 1/4 delta function, theta is equal to 15, plus 1/4 delta function, theta is equal to 17, plus 1/4 delta function, theta is equal to 20. So that's your total prior. Let's just be real careful here, and I'll tell you a few more things. This is a common mistake that I see being made. What's your prior on your null? So this is the prior on the total space right here. This is the null part. This is the alternative part. So what do I write down here?
Delta theta.
Delta theta is equal to 10. I'm good with that. What about this?
1/3 the
Very good. So you have to renormalize it. So your Bayes factors should have 3's pop up in them and stuff like that. So this will be 1/3 delta function theta is equal to 15 plus 1/3 delta function theta is equal to 17 plus delta function 1/3 on that delta function 120. So they have to be normalized. Remember, if I took the 1/4 right here and the 1/4 up there, they wouldn't be weighted right. You'd be implying something different than uniform on your weight on all of those things. So I think this is the sensible prior. Without any extra information, I would pick it to be uniform probably. Does that make sense? The hard bit is when you integrate over this, it's going to take on positive mass at 3 places. Just like this thing took on positive mass just at 1 place. So the integral will evaluate to the sum of 3 things. Just remember, you can just separate your integral. You have an addition sign inside of your integral. You can just factorize it into 3 separate integrals. And you'll have 3 separate integrals that kind of look like this one that we were touching. You're going to have the sum of those 3 things, and it's going to be numerically unstable. The reason why it's numerically unstable is there's model misspecification. So you're asking this question, is theta 10? And you're also presupposing it all came from a normal distribution. It didn't. It came from 4 different normal distributions. And so your hypothesis is partially correct, but your model's totally wrong. So the Bayesian will end up picking the theta that's closest to a theta that explains the data out of a normal distribution. So even the Bayesian is telling you posterior probability is climbing to 1 on one of these. Do you know which one it's going to climb to 1 on? The 15. Do you know why?
Because the overall average is like 14.
Yeah, so the overall average is closest to 15 out of all of those. So if you do this, it's going to say which of these 4 candidate means is best. So when the Bayesian is explaining something to you, they're saying compared to everything we've entertained. So if your alternative is calibrated badly, i.e. you're saying it could have been one of these 3 things and your model's misspecified, while a Bayesian might tell you posterior probability 1, the real question is compared to what? So again, it's just making a direct comparison against something. P-value thing, I think, is I think they're the winners in that example, that it says all of them look bad. So p-value is vacuously small. It's not because of the hypothesized value per se, it's because of the model too. So when your p-values are small, it's telling you that something about your model specification, whether or not it's your hypothesis or otherwise, doesn't look very true. How much do you think about that in terms of a degree of belief? You probably need to entertain how many sample points you've seen in the first place. That brings us around to that whole conversation. I'll try to be better tomorrow and explain that whole thing about Z in N that we were having that conversation about before, but it ties into all of this. Something to think about. So what is a p-value telling you? Something about misspecification. How does that translate to belief in that thing? I don't think it does directly. I think it's part of the equation. What is a Bayesian telling you? A Bayesian is saying out of all the things we've compared to each other, this is the one I believe the most. It doesn't mean that all of the things that you've compared even has the correct thing in there. And so I think when we do hypothesis testing, we need to be making meaningful comparisons. And the whole thing is, what is the comparator group? That's what I always think. Anytime I see any statistical analysis, is what are we comparing to? So, and is that a meaningful comparison? You see this done all the time. And so if they pick the comparator group real badly, the analysis doesn't mean so much. I'll tell you one. Let me turn off the camera for this one. Years ago,